All right, let's get started. So I don't remember if I showed this last time. I forget what sections I showed what to. But once you're done with the syllabus, you've read everything, you know what the syllabus is all about, collapse it. That'll stay collapsed on refreshes and everything until you uncollapse it. So if you got to peek at the syllabus again, peek at it, and then collapse it again, so you don't have to scroll through all this every time you want to look at the course schedule. Same with the project. We talked about all that. Let's collapse it. Then week one's right at the top of the schedule. I always have at least one student who finds that out mid-semester, and they say how much scrolling they wasted by not knowing that. So just want to make sure that's clear. Okay, so we didn't get to any slides last time, so let's do Monday's slides, and then we'll do as much of today's slides as we can. There's time built in here where we can get caught up, so I ain't concerned. You shouldn't be either, but let's get into it. Actually, we had a lot of logistical questions. Anybody have questions about the course before we get into it? Anything about the grading, project, homework? Yeah.
I know there's some people that were confused about like the expected deadline and like the final deadline.
Yeah, I did. That was in chat a bit too, wasn't it? I think of the 312 channel. Thank you for bringing that up. I do want to talk about that. So let's make sure this is all clear. So let's go through the expected deadline versus the actual deadline. There was some chat, there was some confusion about that. So the expected deadline is going to be the first time that the TAs will grade objectives 1 and 2 only. These are only for the learning objectives. So those 2 learning objectives will be graded right here. I'm going to have separate assignments set up in AutoLab for these. So there will be an assignment. If you make a submission to the expected deadline, then the TAs will go in there. Any submissions, they'll grade those for objectives 1 and 2 at that point. If you earn credit for those, 1, you're done with the objective, and 2, you earn one of the 8 available expected deadlines if you complete the objectives at that time. So for homework 1, by Feb 20, 9 a.m., I had that one student last semester who was really submitted the first assignment, thought it was 9 p.m. I want to make sure everybody knows it's 9 a.m. It's the on my desk by Monday morning policy. If by Feb 20, 9 a.m., you get objectives 1 and 2 done on homework 1 and you submit for the expected deadlines, you'll get 2 expected deadlines for that and credit for objectives 1 and 2, learning objectives 1 and 2 on homework 1. So you already have 2 of the 8 learning objectives done, the quarter of the learning objectives done, and 2 out of the 8 expected deadlines working towards your first AO. If you don't get those done by then, or even if you do, the actual homework deadline, that's when all 5 objectives are due. So this is the only time the applications are actually due. There's no advantage to doing the application objectives before the expected deadline, except just not having to think about them and not having to worry about them at all. So the actual deadline is when all 5 objectives are due as an actual deadline. I usually call these the actual deadlines for the learning objectives. This is when you have to have the learning objectives done by in order to get credit, aside from late days and recovery opportunities. And this is the only deadline for the 3 application objectives on each homework assignment, aside from your late days. Now you have up to 4 late days to use. So this deadline, you can extend all 5 objectives by 1, 2, 3, or 4 days. Please don't use all 4 of those on homework 1. That's setting yourself up for a bad time. In my opinion, by the way, it may be too early to say this, but in my opinion, homeworks 2 and 3 are the most difficult ones. Homeworks 1 and 4 are much easier, and homework 1 is easier than homework 4. So don't use any of your late days on homework 1 if you can help it. Save those for homework 2 and 3, and if you use them all on homeworks 2 and 3, you should be all right for homework 4. That's just my kind of advice for approaching the homeworks of the course. But this is the deadline. If you don't complete the learning objectives by this deadline, or the application objectives, you can use your late days and still work on those up to 4 days late if you want to use all 4 on the same assignment. If even after late days, or even if you want to save your late days, the logistics of this, I think will get a little messy. I'm hoping we'll keep it as clean as possible. But you can not use your late days and still not have the learning objectives done and use a recovery opportunity to get another chance at those. The TAs and I had a meeting last week just talking over the logistics of this. The recovery opportunity usage, the way it's worded in syllabus, is a bit off because there are some logistical problems with this, is you won't know if you didn't finish the learning objectives until about a week later when we finally get grades out. So you won't know if you need a recovery opportunity until after the 1 week, and if you're using a recovery opportunity for a 1 week extension to bring you up to that day, that doesn't make sense. So the recovery opportunities will be 1 week after, let me be precise about this. After 1 week after the deadline, you'll get an additional week after that. Let me stick to that way. I think that's what makes the most sense. And then we're guaranteeing that we'll get grades out within 1 week after the deadline. So if we get grades out earlier, you'll just get extra time. So if grades come out and you didn't get credit for both of the learning objectives, you lose 1 or 2 recovery opportunities, and you'll get another week after grades are out. And if we get grades out earlier than 1 week, you'll get a couple bonus days there. I hope that cleared things up. I feel like that might have been more confusing. Get all your objectives done before the expected deadline, and then you don't even have to think about any of that. It's the best strategy. Then you just treat your late days as extra days to work on application objectives. But your late days work for all 5 objectives. Your recovery opportunities are only for the 2 learning objectives. Are there any other questions on that? Are there specific questions? Yes?
Is there any benefit to not using
No. So is there any benefit to not using late days? Late days and recovery opportunities, there's no benefit to saving those up. If you have those on the last day of classes, they just vanish. No advantage. I did one semester when I had recovery opportunities. I had an incentive to not use them, but it just caused so much. Students were hesitant to use them, and they had to use them to pass. This was in 116, not 312. But students were hesitant to use them. They had to use them to pass. But then I would get all kinds of emails like, I used my first recovery opportunity, but I have this and this excuse. Can I get that waived or anything? And I'm like, you have 3 more. What's the problem? Well, you gave this incentive, so I don't like doing it just because it's kind of a headache. I want them to be there for you to use and not disincentivize using them. Because sometimes you have reasons why, you got other shit to do. Like, you don't want to be spending your time a certain week. You got other stuff to do. You don't want to be spending your time on 312. Just use a recovery opportunity. I don't want to disincentivize using them. Okay, any other logistical questions before we get into content for the rest of the semester? Let's do it. This is the first time we're doing slides in this course, right? Yeah, we didn't get to any on Monday. So so when I do slides, you'll see me do this at the beginning of each lecture. I'm going to download my slides from the course website. I'll have the slides link for each one. I'm always going to download those slides, even when I have them downloaded 5 times, as you can see. Even though I have them downloaded a whole bunch of times already, I'm going to download them off the course website just to guarantee that I have the same slides that you have access to. This bugged me as a student. Sometimes the instructor would have an updated version of the slides, and they never updated their course website. I do that to hold myself to making sure that the most up-to-date slides are on the course website. I haven't updated these slides since last semester, so it doesn't apply to this lecture, but I do that just as a show of faith, like, hey, I have the same exact slides. The slides I'm using are the same exact slides, bit for bit, that you have access to. Let's talk about the internet. So if anybody gives like a one-line definition of what the internet is, they'll probably say a network of networks. It's a network of networks. That's what it is. I want to talk about what those networks are. I'm going to find 3 different types of networks and just give like an overview of how this thing we call the internet works. So one network that you're probably very familiar with is a LAN, the local area network. You have your router in your house, usually a wireless router plus switch all rolled into one. and that gives you access to your LAN to all the devices within Wi-Fi range, or if you plug in the Ethernet into the thing, it gives you access. We have a LAN here at UB. We have access points all over campus, and we're all connected to one big LAN. So LANs can get pretty big, all of UB in this case, or as small as just your house with a couple of devices connected to it. This is usually what we actually connect to, and this is one of the only cases where we're using wireless technology, aside from like mobile. I'm not going to talk about mobile stuff. This is where the internet uses wireless connections for my laptop to connect to probably this access point right here. It's wireless, and then after that, there's a wire going to some server room on UB, presumably, and then connected to. Technically, that's incorrect the way I set that up, but and then at our homes, at least, connected to an ISP. So the next network, the network that our LANs are connected to, are going to be the ISPs, the internet service providers, or the bad guys usually. We usually tend to not like our ISPs. I'll include myself in that. They provide a great service, though, but I don't know. I don't want to get into that. But anyway, our ISPs are connecting us at more of like a neighborhood level or a city level. They can get pretty large, but we'll plug into our ISP's network, and you can see these cables. Usually they're buried around here, but if you see the utility poles, some that's power and some that's going to be internet, among other things. But some of those lines are going to be internet, and you literally plug in to those wires, whether they're in utility poles or underground. You're plugging your modem into those wires, and then the modem translates their coax signal into Ethernet. You plug the Ethernet into your router, then your router blasts your Wi-Fi across your house. And that's how we're plugging in, that's how we're connecting to the ISP, is when you order a service, you call up Verizon Fios and you say, hey, I want internet. They send someone to your house. They either go up into the poles or go underground, and they run wires to your house and literally plug in. You plug into their network, which is the same technology, well, kind of different. I just mentioned different cables, not Ethernet cables, but same kind of technology that you have with your LAN. You're plugging things in. You're plugging your router into other devices, aside from Wi-Fi, of course, but any Ethernet devices. Same thing here, except they're plugging in houses. They literally have wires going around plugging houses into their network. But it's the same technology. Those wires go to their routers to form their large network. Same idea of what you're doing with inside your house, though. And then Tier 1 networks. This is, I like to call these the ISPs for the ISPs. This is, or the backbone of the internet. The Tier 1 networks are the networks that are connecting cities to each other, traversing large spans of land and spanning entire continents, entire countries. These are our Tier 1 networks. The ISPs are going to pay Tier 1 networks for Tier 1 access, just like we pay the ISPs for access to their network. Then the ISP, we'll have local ISPs in certain areas of the country. Like they don't have, I always forget the Spectrum. They renamed it from Time Warner. It's still Time Warner in my mind. But Spectrum, like they don't have that out west, as far as I know at least. Maybe they expanded. And we don't have, I shouldn't have backed myself in the car. I forget what they have, other parts of the country. But they have different ISPs than we do. But all those ISPs are plugging into the Tier 1 networks, and the Tier 1 networks are the larger networks connecting entire regions and countries and continents. These networks have peering agreements with each other, so they all agree to use each other's networks. I like to think of this as more of an accounting thing, where they could charge each other to use each other's networks, the Tier 1s of their own networks, but the accounting would just be absolutely crazy trying to figure out how much data each Tier 1 used of other Tier 1 networks and stuff. They say screw all that, and they have peering agreements where they just say, we can all use each other's networks free of charge. So because of these peering agreements, the Tier 1s, all of the Tier 1s, all these companies and all their networks act as just one large network, since they can all just use each other's wires, use each other's cables free of charge. And again, this is the same technology that our LAN's using, same technology that the ISPs are using. It's large cables that span for hundreds, thousands of miles and connect all our cities together. And then they connect to each other and form one large network. And this is, I already mentioned it, backbone of the internet. If anything could be called the internet, I would say it's this, the tier 1 networks and these peering agreements forming this one large network. That really is the internet. And then the ISP plugs into the tier 1 networks and lays cable through our cities and connects our houses. And then in our houses, we have our routers, which helps us connect. Just follow a couple of steps to get to that tier 1 network and connect to any device that's connected to those tier 1 networks through their own ISPs, which means we can connect to, most people on the planet at this point through these connections. And some of these companies you've probably heard of, some of them you might not have. For example, like Verizon, they're a tier 1, but they also act as an ISP in certain areas, including our neighborhoods. AT&T you've probably heard of, but some of these you haven't. L3 Communications, Level 3 Communications is, I believe, the largest tier 1 network. And unless you've looked into this stuff and studied this stuff before, you probably never heard of them. I never heard of them until I started looking up what's a tier 1 network, how does the internet work. But they probably handle your data. Whatever you're connecting to right now, they're probably handling that data at some point. Yeah.
So for internet service providers that do like fiber optic, are they acting as tier 1 networks?
It depends. There's not a one-to-one. Like a tier 1 can use fiber, or an ISP can use fiber without being a tier 1. Verizon happens to lay fiber. They just use fiber, and they happen to be a tier 1, but it's more coincidence than... I mean, really, they're just all... If they're laying new cable, it's going to be fiber these days. But yeah, you can lay fiber without being a tier 1. Tier 1 really just means you're connecting, like, crossing vast amounts of land. There's an implication here. So when the ISP comes to your house and you plug into their network, they run 3 wires out to your house and plug you in. But I also mentioned that ISPs pay tier 1s for internet access, and tier 1s have peering agreements to each other. The implication is that those networks have to plug into each other. That gets messy, that gets crazy. There's cables everywhere. Like, this takes a lot of space. And takes up, I don't think it's this whole building in Manhattan. I believe it's the 6th floor, like the entire 6th floor is their internet exchange. But they have buildings filled with just cables that are plugging these networks into each other. And it gets complex, it gets messy. You need a lot of cable organization, as you can see. But my point of this is, it's still a very physical thing. It's still cables. Even though I don't have any internet plugging into my laptop right now, it's wireless to that access point. But after that, it's wires, it's cables, it's fiber, still probably a bit of copper. But it's physical cables from here to one of these to get to another network, to bounce around all the way till whoever I'm connecting to, it's Wi-Fi again, and then Wi-Fi for just a little bit of that trip. But when I showed you the tier 1s, I only showed you the United States. As we all know, the internet's global. So how do we span continents? How do we get to another continent with the internet? What was it? I thought someone said.
Somebody said underwater.
Underwater. Hell yeah. It's just big freaking cables. Literally giant cables that just sit on the ocean floor. This is crazy. I never thought that would be the answer. But it's still physical. It's still cables. It's still the same technology. Like, we're running Ethernet cables. It's still, not Ethernet. It's going to be fiber at that point. It's going to be huge cables. But it's still just, how are we going to connect to Europe? I don't know. Let's get a giant cable, plug it in on this side, run it over the ocean, and plug it in on the other side. That's how the internet actually works. It blows my mind still. It's all physical. It's all cables. Of course, there are some satellite providers, and we do have Starlink that's hopefully becoming more popular. Hopefully that takes off, and we can start using Starlink. So the future looks pretty cool. Right now, the internet is very physical. It's physical cables plugging in. If I send a message to someone in Beijing, wireless, cable all the way to their home in Beijing, you can follow a physical cable that entire distance, and then Wi-Fi for the last couple feet again. Everything else is physical. It's a very physical thing, the internet is. Just cables plugging in everything to each other. And then routers connecting those cables to each other to determine how to route packets through the internet, which we'll talk about in a bit. Including some, I almost said private companies. The tier ones are private companies. Well, they might be publicly traded, like Google's publicly traded. But some organizations that are not tier one networks, that's the way to word it. Some organizations that are not tier one networks also have vast networks. Google has a lot of cable that they run to connect, across land, but they also have their own submarines. Is that the word? Man, why am I blanking on the word? It's probably on the thing. Submarine cables. They have their own submarine cables that lay on the ocean floor. Google said, it's worth it to, instead of paying these tier one schmucks, we're just going to lay our own cable. And they have their own cable in a vast network. This is why when you load up YouTube, it's typically loads faster, even with way more user base, typically loads faster than other video streaming services. Some streaming services lag quite a bit, the quality will go down. Google's got that speed because they laid their own network. They have a huge network that's, probably equivalent or even bigger than a tier one network, but they just use it for Google services. And of course, they sell access to it. Amazon does the same thing. That's why you can get AWS, and you can host your web services, and they can provide that service cheaper than a lot of competitors. It's because they built so much infrastructure of their own. They're not relying on the tier one networks to be able to do that. Google too. I'm blanking on their service, but Google, you can pay them, and they'll let you use their network as well. So what's the destination? All these wires are connecting us, but it's one thing to connect to other people directly, but usually what we're doing is connecting to a web app and communicating through a web app. I don't know if we ever send each other messages directly. You go to Twitter and send a DM or whatever cool social media app y'all kids are using these days. I don't know, but I think I'm behind on it. What is the cool one now? It's not Snapchat anymore. It's Be Real? Okay. I'm not cool enough to know these things. But, yeah, I didn't know what Riz meant until Monday. But we're usually communicating through an app, through an internet service. And those are going to be hosted in data centers like this one. This is the one in Lockport. This is a Yahoo server farm in Lockport, the closest one that we could find. In 15 minutes, you could drive to this place and probably not walk up to it. They might kick you out. But you can see it from the road. It's an impressive sight to see one of these things in person. These buildings are just filled with servers, and it's just tons of computing power plugged in, usually directly to a tier one. This is why I almost misspoke and said this is going to connect to an ISP. It doesn't. UBs connects directly into a tier one network. They don't mess around with Verizon Fios or Spectrum. So this is going to be plugged in directly to a tier one, and that's how we're connecting to apps on the internet. Huge amounts of processing power. This isn't the same data center, but this is what's going to be inside there, just massive amounts of computing power and racks and racks and racks of servers. If you've never handled a physical server, I don't know, I feel like that's something that all of you would have done at this point, but I also feel like I'm probably way overestimating on that. So let me explain it for a second. These are all servers. They're computers. They run on the same type of hardware as our laptops, as our desktops, but they're shaped differently to be able to fit in these racks easier, and the racks are designed to keep them cool. Other than that, they're the same hardware. It's usually different models of hardware. They're designed for server-specific things. Like, you don't need no graphics card in this thing. So they get different processors with more cores, typically, more RAM capabilities, but it's all the same idea. They got processor, RAM, hard drives, things like that in these servers. And all these servers host your web apps. For example, like you could technically, theoretically, run YouTube on a single machine, but it wouldn't be able to handle the load. It wouldn't be able to handle streaming millions of simultaneous videos, absolutely massive amounts of load. Just the amount of data that's being uploaded that needs to be stored on a hard drive somewhere, processed and stored, encoded. They encode every single video that's uploaded. Massive, massive amounts. They need a lot of computers, so there's just racks and racks and racks. Google has multiple data centers, a lot of data centers around the world, a lot of computing power. So we have these physical cables plugging us in to these data centers. These data centers get our messages, processing millions, billions of messages, and enabling the internet that we enjoy, the internet that we know. But it's really, at the end of the day, it's a bunch of computers connected by cables and a bunch of routers connecting cables. That's what it is. That's what the internet is. Unfortunately, no magic. It was proposed to rename this class Dispelling Magic, ruining all your childhood dreams. Everything's gone. We're just going to tell you how it works, and it's not super crazy. Like, it's just cables plugging in computers. That's how it works. The rest is what else we'll learn in this course. But that's the internet itself. So how are these cables actually used? Obviously, I'm oversimplifying. So how do we actually use these cables and send messages around the world? Well, first, the internet protocol. This is the protocol of the internet. They nailed the name on this one, internet protocol. The internet, the protocol of the internet. Everything that's ever sent across the internet is using the internet protocol. If it's not using the internet protocol, I would say that's not part of the internet. This is the internet. So the internet protocol, the most important part of IP is IP addresses, which I'm sure you've heard of. You've all heard of these at one point or another. So we have the standard IPv4. You can look up the link to see exactly what's defined in IPv4. And this allows us to send messages to each other. I won't belabor the analogy, but your IP address is very similar to your mailing address. Somebody wants to send you a letter, they write your IP address on it, they throw it off in the internet, and the routers are going to send it, make sure it gets. They won't make sure it gets there, but they'll do their best to send that message to whoever you're sending it to, or whatever data center you're sending it to. In most cases, you're sending a message to a data center that's running a service. IP works on packet switching, which I won't get into all the gritty details of this, but this was a revolutionary decision to use packet switching as opposed to, oh my goodness, I'm going to blank on the name. The other kind of the other kind. So the difference is the other kind that I can't think of the name of is if you wanted to connect two computers together, you would have you plug them into each other, and there's a connection, and that connection is established, and that wire, so they're already plugged into each other through the internet. But like there would be one path, one conductor that they would use. And all message sent over that conductor for that period of time of that connection is used by just those two people for that one connection. Packet switching says, nah, let's not do that. Let's share all the conductors, let's share all the connections, and just switch packets. So each packet is a very small, limited size in the order of kilobytes. And whenever you send a message over the internet, it has to be contained in one of these packets. So if you want to send gigabytes of data to somebody, it's going to be chopped up in these packets. And then when you have a bunch of packets that you want to send, somebody else has a bunch of packets, these messages are going to be packet switched, meaning one of this person's packets will get through, one of your packets will get through, one of this person's packets will get through, and we can all share the wires without having to have anybody monopolizing any of the connections. You don't want somebody establishing a connection using a full conductor and then just saying like, hey, what's up? And then like not saying anything for a while and, oh, what's up? Like how I don't think it works like this way anymore, but that's how the old telephones used to work. Like you would use one of your telephone lines. Then if you wanted two people to be able to talk, you need two lines. Back in those days, it might be at a point where you never even experience that, which is weird for me to say. But packet switching lets us use all these cables, share all these cables, and it makes the internet very efficient, and most importantly, allows it to scale. If this wasn't the case, we would never be able to scale to this many users. We wouldn't even all be able to connect to these access points simultaneously, because there just wouldn't be enough. There'd be so much wasted bandwidth. All right, packets have a header and payload. Header, most importantly, source and destination IP address, along with some other information. And the payload, that's the good stuff that we're interested in. And the payload, the routers of the internet don't care what the payload is. It's just bytes to the routers. But we care, and we're going to implement additional protocols inside the payload of our IP headers. I almost deleted this slide. I'm not going to talk about it. IPv4 that I mentioned earlier is, you've probably seen these before. It's 4 digits, 0 to 255, separated by dots. That's just for us to read. Realistically, it's just a 32-bit value. The separating by dots is just to make it more human readable. To the computer, it's a 32-bit value, which means there are about 4.3 billion IPv4 addresses, and at one point, there were more than that many devices connected to the internet. Not even that many people, but like, I have multiple devices right now. I'm sure most of you do. We ran out. We ran out of these, and we needed something else. So in come IPv6. IPv5 didn't make the cut and never saw widespread implementation. And this uses 128-bit addresses. So when they came out with IPv4, they said 32 bits, 4.3 billion. We're never going to have that many devices connected to the internet, like way back before the internet was popular. We're never going to see more than that. And we know now that they were naive. We definitely hit that number and then some. But at risk of making the same mistake, I'm going to say this is enough. 128 bits. I don't think we're ever hitting that number and running out of IPv6 addresses. So I think we're good on IP addresses. We have plenty of them. This number is larger than the number of atoms in the known universe. I think we're going to make it. We're going to be okay. So most routers of the internet, I think I could say all by now, have to support both IPv4 and IPv6. If they don't, if they only support IPv4, I don't want to go down that rabbit hole, but there's like IP tunneling, and there's ways around it. So if you want to send a message to another device connected to the internet, you know their IP address, and you send a message to that IP address. The routers of the internet send that message to that IP address, and that other device gets that message. We don't like memorizing these, so we have DNS. This is, I can type google.com, buffalo.edu. The DNS lookup tells me the IP address, and then my browser sends a message to that IP address. So you never actually send something to buffalo.edu. You just get a DNS lookup. The DNS server tells you this is the actual IP address. The IP address of the DNS server is in your machine already. When you set everything up, like that just happened. You don't have to actually worry about that unless you want to. But that IP address is already known to your device, and then it shoots off that message to the DNS server. It says, here's the IP address you're looking for, and then a message to that IP address is sent. That way we don't have to memorize. I think this is Google's IP. I forget what these are. We don't have to think about what the IP addresses are. We just remember the domain names. That's just a human creature comfort. So just things to make our lives easier. And this is what an IPv4 header looks like. Most importantly, source and destination address are both on that IP packet. And then the payload of your packet, what you're actually sending to that person, is going to be down here. Yep.
Who owns like the DNS servers? Who gets which domains?
Good question. I'll be able to give you a partial answer. I might hit the end of my knowledge on this one. But who runs the DNS servers? Whoever wants to start one. If you want to start your own DNS server right now, you can start it up and then start telling people, hey, here's my IP address for my DNS server. You get a static IP address and then just tell people, hey, that's my IP address. I got DNS. I implemented the DNS protocol on this thing. So anyone can. There are several common ones when your device is going to have some that it already knows and likes. I believe whoever's writing your operating system would set that. I believe that would be an operating system level config. I know you can change them at your operating system, but some software will override those, and I know it gets messy a little bit. Who decides what domain name maps to a certain IP address? So you can update DNS records. Like if you have an IP address and you buy a domain name, you say, hey, I want to update the record for this domain name to this IP address. Where my knowledge hit the end of my knowledge is how that exactly propagates through all DNS servers. If there's like one central location that if you run a DNS server, you go there for the ground truth. I don't know exactly how that works, or if one DNS server gets that information and just tells all the other DNS servers and they just have ways of communicating that. I'm not 100% sure on that one. I know when I buy a domain name, I use Google Domains to handle my domains, and I just tell Google, hey, map this to this IP address, and then all DNSs around the world after a certain amount of time will just have that updated. Like Google has their own DNS servers. If you want to use Google's instead of your default ones, 8888. They made it really easy to memorize. 8.8.8.8 is their DNS server, or 8.8.4.4. Yeah.
If I'm buying a domain that nobody owns.
That's another one that I've wondered this for a while. I don't know exactly how that works. I believe there is an organization that is the ground truth for that. You can't talk to them directly, so you go through a domain. Whoever's selling the domains. Again, I buy mine from Google. So I would give Google like $12. I forget what the rate is right now for a .com. And then I think they give like $8 to the other people and actually reserve that and get that for me and then tell me that I own it. But I forget what that organization is or if I'm completely misremembering it.
So is there no way I can like skip?
There's definitely a way, but is there a way you could do that without starting a business and filing all kinds of paperwork and spending way more money than it's worth? Probably not. You'd have to like be a Google, I would think. Or at the very least, apply for all kinds of licenses that are going to cost tons and tons of money. I'm speculating there, but I would imagine that's the way it works. A lot of things that are like that, when you have a service that doesn't want to deal with millions of customers, they just want to deal with a small group of customers, dozens or so, they'll just make it prohibitively expensive to join that group, and then just those customers can go out and be the actual salespeople. It's typically how things like that work. So I'm just transferring that over to DNS. I'm pretty sure that's how it works. Any other questions? These are good questions.
Yeah, how do routers determine which next router to send packets to?
How do routers decide?
Yeah.
That one I won't answer at all. I'll answer it like this. Take Modern Networking Concepts, 486, I believe. I have a pitch for it on my last slide. There are lots of algorithms to decide that. I don't remember any of them off the top of my head. It's been a while since I took that class, and I never cared in a long time. I'm happy that it works, that it does happen. But there are a lot of complicated algorithms to figure out the next steps and update their forwarding tables. Modern Networking Concepts will go into all kinds of detail on it. But yeah, that's a good segue back into the slides. So the routers of the internet don't make sure that your messages get to its destination. I almost misspoke on this one. The routers of the internet don't say, okay, I have a message, it's got to get to this destination IP, let me make sure it gets there. What the routers of the internet do is send it to its next destination, or what we call next hop. So a router of the internet has its forwarding table. It says if the prefix of the IP address starts with one of these, with this prefix, I'm going to forward it to this router. If it starts with this prefix, I'm going to send it to this router. It does prefixes because it doesn't have entries for all 4.3 billion IP addresses. It goes by prefix, so anything starting with certain numbers, it'll forward to certain routers. Sends it to its next step and then forgets about it. That router's like, I did a good job today. Yes. Just sends it off and whatever. This is good. I see this as a good thing at least, because it's designed for speed. This is fast. If there were all kinds of checks and balances and everything, it would take a lot longer to get a message to where it's going. So IP, the internet itself, just says, send it and forget about it. I got this queue of 1 billion packets that I got to forward. I'm just going to forward them as fast as I can and forget about them. So the internet, that is the internet. That's the internet protocol. The internet is very unreliable. We can't guarantee that we're going to get a message to where it's supposed to go. So income, TCP, usually hear these together, TCP, IP. We really need both of them to make the internet useful. But IP is the internet. TCP is going to make the internet more useful, more importantly, reliable. So when a packet is sent by a router, there might be a multitude of reasons why that packet doesn't get there, and we call it a dropped packet. This happens all the time. Packets just don't make it to where they're supposed to go for a multitude of reasons. So TCP says, all right, we can't have that. We want to actually get our stuff. So TCP, in addition to the internet, usually in your browser is going to handle all this stuff, or your whatever library you use in your homework is going to handle this stuff, but not the internet, not the routers of the internet. Nothing connecting these cables is going to do anything, not the Wi-Fi. This is on your device at this point. So when messages are being sent from your device or received from a device, those devices have to speak TCP. The internet does not speak TCP. The internet at large only speaks IP. So on the ends of the connection, and I'll call them client and server, it's usually the connection. We have a client connected to some server somewhere. We're going to have a three-way handshake to establish a connection, a TCP connection. This three-way handshake, there's 3 messages that need to be sent. First, the client says, hey, server, I want to establish a TCP connection with you. They're going to do this by sending a random number M. The server is going to respond with M plus 1 and their own random number N, and the client's going to respond with N plus 1. So this seems kind of pointless at first, but what they're doing by sending a number, having the other side read that number, increment it by 1 and send it back, proves that, 1, you're speaking the same protocol. You both understand that this is TCP. You knew where to read that number, how to read that number, how to decode it, add 1 to it, perform an operation on it, a very simple operation, just adding 1, but an operation, and then re-encode the new number following the protocol properly. So at this point, after the three-way handshake, client and server both have reasonable assurance that the other side speaks TCP properly, and we don't have mangled connections where they're speaking different languages. They both speak TCP because they did this three-way handshake. At this point, a connection is established. Client and server just agreed to commit to a TCP connection together, and now we can start transmitting data. Now instead of just firing off individual packets into the ether and hoping they get to where they're going, now we're going to have a little more structure to that. We have an agreement that we're going to send each other packets, and when we send those packets, each packet is going to have what's called a sequence number attached to it, which helps each side identify if there was a dropped packet. If I get sequence number 0, 1, 2, and 5, I'm going to say, hey, where's 3 and 4? Can you resend 3 and 4? I seem to be missing some data here. And you usually tell what the last sequence number is. Hey, you should expect sequence number up to 10. Well, then I'm going to say, hey, where's 6, 7, 8, 9, and 10 as well? And I can request resends. So when there is a dropped packet, we can detect and then request a resend to get that extra information, to get that information that we missed. TCP also establishes the idea of port numbers. Whenever you hear about port numbers, that's a TCP thing. I believe UDP also does port numbers. I think they'd have to. It wouldn't make sense to not. But port numbers is an IP thing, or a TCP thing, in the context of this course at least. It's the only time we'll see them. And this allows you to have multiple connections to multiple other devices simultaneously. So instead of just sending a bunch of packets, getting a bunch of packets, what if you have 10 tabs open, you're connecting to 10 different servers, and they're all sending you messages, you get this mess of packets? Instead, TCP says, well, each connection is going to get a different port, which is just a number. There's no magic here. But they're going to get a different port, and then if I get messages with this port number, I know it's from that server. If I get a packet from this port number, I know it's from that server. And you can have multiple connections simultaneously. Up to 65,000 connections you can have, 65,000 different other devices on the internet, all with their own TCP connections simultaneously. In your code, you're going to import a TCP socket library, and everything we just talked about will be handled for you. That's why I like to cover these slides day one, even though it's day two that I'm getting to them this time. All of that stuff is done for you. I didn't get into the nitty-gritty details at all. That's because you don't have to code them. You're going to import a library. It's going to establish, you're going to import a TCP server library. It's going to listen for client connections, establish those connections, and you'll be able to communicate over those TCP connections. When you receive a message or send a message, the library is going to do all of the three-way handshake. It's going to do all the sequence numbers. It's going to do the drop packet resend requests. It's going to handle all of that for you. And then where we're going to start is with HTTP, which I guess I won't get to start until Friday. And if you want to know more about the stuff we did, the rest of this class, I'm just going to say TCP/IP works. It just works, and we're going to focus on cooler stuff, in my opinion. I don't know. Actually, this stuff's cool too. But if you are interested in that and you want to learn more about how TCP/IP, UDP, all kinds of other things work, and much more, Modern Networking Concepts has you covered. They have so much good content there that will tell you all about how that stuff works. We're just going to assume it works and then use libraries for it. 46, is that accurate? I don't really have time to talk about HTTP, right? Oh, and there's my alarm. So don't pack up yet. We got one of these. Woo! So we have our first lecture question. You should all be in AutoLab. If I refresh this, my notes should go away. The only thing there is the lecture question for today. Select your answer, tell me you didn't cheat, and then submit. You only get one shot for lecture questions. I'll be pretty lenient this week. If you have any technical issues especially, send me an email. We'll work it out. We're still before ad drop, so I can't hold you too accountable. But yeah, it's our first lecture question. I'll typically do the lecture questions right at the end of lecture. And once you submit the question, you're free to go, and I'll see y'all Friday.